All right, in this section we are talking about polynomial functions, which this is the technical definition of a polynomial, but all a polynomial is, you know, something like f of x equals x to the fourth minus 3x cubed plus 5x minus 1, you know, something like that, where every term, the variable's exponent is a whole number, a positive integer, and yeah, so this looks a little more familiar than, say, this mess right here. This is just the technical version. The a sub n, which is this number in the very, very front, that is called the leading coefficient. And it tells us some things. Leading coefficient. And I should say this, anytime you have a polynomial, you want to put the terms in order from biggest to smallest. So you can see how I put x to the fourth in the front, and then x to the third. This right here would be x to the first, and then the constant on the end. So this first little section, all they want you to do is state the degree of the function and the leading coefficient. And when I say degree, I'm talking about the highest exponent on the polynomial. And let's actually start on the bottom and work our way up, because this one's kind of a weird example. So the degree of this is 5 because it is the highest exponent on our variables. And the leading coefficient, that's the number in the very front. When it's written in standard form, it would be 9. So the degree of this one would be 4. Highest exponent is 4. Leading coefficient is -3. Next one, the degree is 3. Leading coefficient is -1. The degree of this is 2. Leading coefficient is 12. If there's not an exponent on your variable, then remember that's a 1. And -5 is the leading coefficient. And if you ever have just a plain number like that, the degree is 0. And leading coefficient would be 4. All right, so now we're gonna draw out the basic polynomial functions, their parent functions. The constant parent function is f of x equals a number, we'll just call it c. So for example, this could be f of x equals 2 or whatever. A constant function is a horizontal line. So this is a horizontal line, and so if you had f of x equals 2, for example, it would just be straight across like that. I accidentally put a little bit of bend in that. It should be a perfectly horizontal line. The linear parent function is x, y equals x, and y equals x, it has a slope of 1 and it goes through the origin. So it's that perfect diagonal line like that. The quadratic parent function, we talked about this a few weeks ago. Y equals x squared, and it makes this U shape like that. Cubic function, that is x to the third, x cubed, and it looks like this. This tail points up, the left tail points down, like that. Oh crap. There you go. Sorry about that. So x squared makes the parabola shape, x to the third is this. Okay. The quartic parent function is x to the fourth, and it is shaped very similarly to the x squared graph, except it's a more narrow parabola. So it's a little steeper because it grows faster since it has a higher exponent right here. And then same thing with the quintic or quintic, or however you want to pronounce it. X to the fifth, it is just a steeper x to the third graph, basically, like that. So one thing I want you to notice is that every time you have an even exponent, like the 4 here or the 2 right here, both tails point in the same direction. So if it's even, they point in the same direction. If you have an odd exponent, like x to the third, this is x to the first, that's odd. And then if we come up here, x to the fifth, those tails point in opposite directions. That one points up, that one points down. So that is an important observation to make. And so when I look at this, it wants us to determine the end behavior. And so all you have to do, it's something called the leading coefficient test. All you have to do, oh, well, I guess it says use the graphing calculator to determine the end behavior. So on the graphing calculator, we'll go to the y equals screen, and we'll type in this function. So 4x to the fourth plus 6x to the third minus x. When I hit graph, there it is. Okay. Remember this little statement right here, as x approaches infinity, this means where's the right tail going? As x approaches negative infinity, that's saying where is the left tail going? So the right tail is this one. It's going up for forever, up to infinity. The left tail is also going up to infinity. Okay, if I type in the next function, negative x squared plus x. Okay, my right tail is going down to negative infinity. My left tail is going down also to negative infinity. All right, 2x cubed, graph. My left tail goes down to negative infinity. My right tail goes up to infinity. Okay, negative x cubed. My left tail goes up, my right tail goes down. All right, next one, negative 2x squared plus 4x minus 7. Both tails point down, so both are going down to negative infinity. All right, and then the last one, 1/2, x to the third plus 7. All right, my right tail is going up, my left tail is going down. Okay, so again, when you see an even degree, like the 2 here and the 4 here, those tails point in the same direction, so they're the same, both infinities here, both negative infinities here. And then when they have an odd degree, like the 3s, they go in opposite directions. So you can see that one infinity is positive, one's negative, every time you have an odd exponent. So there's this nice little chart right here. If you have a positive leading coefficient and an even degree, then both tails are going to point up, like that. If you have an even degree and a negative number in front, then that means both tails are going to point down. If you have an odd degree and a positive leading coefficient, then the right tail will go up, the left tail will go down. And then odd degree negative leading coefficient, your left tail will be up and your right tail will be down. So as soon as we see this graph down here, they want us to determine the sign of the leading coefficient and state if it has an even or an odd degree. So as soon as I see both tails pointing down like that, I can just look at my chart. Here we go. Both tails pointing down. That means it has an even degree and it has a negative leading coefficient. On number 8, my right tail is up, my left tail is down. So that is this scenario. So we have an odd degree and a positive leading coefficient. Okay, we also need to talk about turning points, and turning points are the points at which the polynomial function switches directions. So, for example, if I start following this polynomial curve right here, I'm going up, I'm going up, I'm going up. Once I hit the top here, then I start going down. So that is a turning point right here. And then I keep going down until I hit here, and then I go back up again. So there's another turning point right there. So this graph has 2 turning points. The first one, if you have a hill, kind of like this one right here, if the turning point is higher than any nearby point, it is called a relative maximum. And it looks like a hill, so it looks like that. If the turning point is lower than any nearby point, it's called a relative minimum. And that would be this one, because see how this point is lower than the points around it? So that is any kind of U-shape spot on the graph. Maximum and minimum values are called extrema. So if you ever hear me use the word extrema, I'm just talking about hills and valleys on the graph. So they want us to use the calculator to find the turning points. And it's pretty easy because you just, well, as long as you remember the functions or the buttons to hit on the calculator. So to do this, we're going to type in this function on the calculator. So x to the third minus 6x squared plus 7x plus 2. And we'll hit graph. So yeah, enter the function y equals, hit graph. It's right here in the top right corner. And if your graph does not look like this, you may need to hit zoom and go down to number 6, or you can just hit the number 6. It'll give you a negative 10 to 10 window like I have. Okay, so to get the relative max, start with that since that's first. You're going to hit the blue second button and then trace, because behind it says calc. See that? So you pull up the calc menu and we're going to find the maximum first. So maximum, hit enter. Notice down here in the corner it says left bound with a question mark. So what it wants you to do is go to the very top of our maximum. This is a max because see how it looks like a hill? Okay, you go to the top of that, you hit the left arrow a few times because you want a point that is to the left of that very top right there. And there's not like a science to how far away you need to go. I just usually hit the left arrow maybe 2 or 3 times and then hit enter. And as soon as you hit enter, this little message at the bottom is now asking for a right bound point. So now we will go back up to the top. Now we need to hit the right arrow 2 or 3 times. So that's good. And you hit enter again. Okay, now the message says, guess where the maximum is. So we will hit the left arrow again, go to the very, very top of the mountain as best as we can, and we'll hit enter one more time. So when you do that, you get the coordinates of the turning point. So the x coordinate is 0.709. We'll just round to the third decimal. The y coordinate is 4.303. Like that. And sometimes you'll have more than one hill in a graph, but in this case that was the only hill that we had, so we only have one relative max. Now we got to find the relative min, which is the little valley right here. So we're going to hit second calc and we're going to go down to minimum this time, And we're going to have to do the same thing. So move your cursor to the very, very bottom of the hill, and we're going to hit the left arrow about 3 times because it wants a left bound point. So hit that a few times, hit enter. Okay, now come back over here, use the right arrow, hit enter, and then guess, it means go to the very, very bottom of the hill, hit enter again. So these are the coordinates of our minimum. So the x coordinate is 3.291 about. Y coordinate is -4.303. Like that. These happen to be the same decimal, but that was just a coincidence, so I don't feel like that's always going to happen. Besides, that one was negative, but okay. Now it wants us to write down increasing intervals and decreasing intervals. So here's how you do that. If I look at this graph right here, we are increasing on this whole piece right here until you get to the top. And then on this part, we are decreasing. Okay, and then we increase again on this part. And the way we get to our intervals is we use our x coordinates where it switches from increasing to decreasing. So if we go back to our little graph here, all right, increasing, so if I'm starting here on the graph, I'm increasing here. And the interval for this piece of the graph would be from -infinity, because this tail keeps going for forever, from -infinity all the way up to the x coordinate of my max. The x coordinate of my max is this. So -infinity to the x coordinate of my max, I'm increasing. Okay? Then on this part of the graph, I'm decreasing. So that goes from the x coordinate of my max to the x coordinate of my min. So the x coordinate of my max was 0.709. X coordinate of my min was 3.291. Okay. Then when I pull this back up, I increase again from the minimum all the way to infinity. So the minimum here, that x coordinate was 3.291. So I've got another increasing interval, 3.291 to infinity, like that. So let's practice a few of these because I know it's a little bit tricky to wrap your brain around. And we also review domain and range in these, so that'll be helpful. All right, you start off by entering this function. So type that into your y equals screen, and remember y equals is right here. Type that in and hit graph. Okay. The domain of any polynomial function is -infinity to infinity. And that's because if you think about all your x values, this tail right here goes to the left for forever, this tail goes to the right for forever, so every single x coordinate will have some point mapped to it. Okay, the range, if I think about the lowest y coordinate, this tail goes down for forever. So the lowest y value would be -infinity. The highest y value would be infinity, because this tail keeps going up for forever. Like that. Now let's get the max and min. So I see we have one of each. This right here is a maximum. This down here is a minimum. So let's get those coordinates. We'll start with the max. Hit the blue second button in Calc, maximum, hit enter. Scroll over with the right arrow, okay, till you're at the very top-ish. Now it wants a left bound point. So we're going to hit the left arrow about 3 times, and we're going to hit enter. Now it wants a right bound point. So we go to the right of the maximum, about right there, hit enter again. Then hit the left arrow, go back to the very top, hit enter one more time. So here's our maximum, and sometimes you'll get like 0.00009, something like that. The calculator is technically rounding. If you see something that close to 2, just call it 2. So our maximum is at 2.4. Now we'll do the minimum. So second calc, go down to minimum. Okay, so this is the minimum, that little valley right there. We'll hit the left arrow a few times, hit enter. Get a right bound point, hit enter. Go down to the very, very bottom, hit enter again. Okay, the minimum is at 0, 0. So those are some points on the graph, and let's go ahead and plot those. So 0, 0 is a point. So is 2, 4. So 2, 4. All right. Now we need additional points because we don't want to just we don't want to just draw some random curve here and make it really crappy looking. So we're going to use the table. So hit second table, and we're just going to get points that are kind of close to our maxes and mins here. So maybe I'll plot this point, 1, 2. I'll also plot -1, 4. And what else will fit? 3, 0. And I think that's the only thing that'll fit on our grid, because at 4 we go all the way up to 16, and at -2 we're at 20. Okay, so be careful when you go to draw these because you want it to look nice and curved. Oh dear. So something like that, and then back down. I mean, it should look like this. So make sure you put arrows on the ends like that. Okay, end behavior. So the right tail is pointing down to -infinity. The left tail is pointing up. That means it's going up to infinity. Now we've got to get the intervals, the increasing and decreasing intervals. So on this, and I should emphasize, you always start here, you go from left to right. So don't get confused, because sometimes people see this arrow and they're thinking it's increasing there, but it's actually decreasing because you go from left to right. So this is decreasing. I'll put a little D here, decreasing. So we're decreasing from -infinity all the way to this minimum x coordinate, which is 0. Then on this part right here, we are increasing. So I put a little I right there. So that goes from the minimum, which is at 0, and it keeps increasing until you get to the top, which that vertex is at 2. And then we decrease again from this point, which that point is at 2, and it keeps decreasing for forever, so all the way to infinity. Okay, let's try another one. Start off typing in the function. Okay. Hit graph. Like I said, the domain is always all real numbers. One tail will point to the left, one tail will point to the right. Range, we don't know the range yet because we don't know this y coordinate right here. It looks like it might be -3, but we need to be for sure. So let's get the relative max and mins first. Oh, I actually see one minimum here and another minimum right here, 2 valleys. So we'll have 2 points here, and we'll only have one max, this one right here. Let's get that max first. So the maximum, hit the left arrow, hit enter, right bound point, and a guess. So 0.5 is the max. Now we gotta get the minimum. So let's get this minimum over here first. So we'll go to the left a few times, like this is fine. Hit enter, go to the right of the minimum, hit enter. Go to the very bottom, hit enter again. Okay, so the x-coordinate is negative 1.838. And the y-coordinate is negative 3. We'll just say 310. Okay, so that is this minimum, which we needed this for the range because that is the lowest y value on the graph. So this is going to be the lower bound on our range. Since it is a filled in dot, we put a bracket around it. The highest y value, these tails point up for forever, so it goes all the way up to infinity. Okay, but we do have another minimum, so we got to do this again. This time, hit the right arrow so that you're way over here. So we need a left bound point, a right bound point, and a guess. Okay, so the other minimum is 1.088, 2.954. Two minimums. All right, end behavior. My right tail goes up for forever. My left tail also goes up for forever. And then let's go ahead and plot what we have. These are decimals, but you can just get as close as you can. They'll be fine. So 0.5 is a point. That's an easy one to plot. This is negative 1.8, so it's almost to negative 2, but not quite. And then we'll go down to negative 3.3. So negative 1, negative 2, negative 3, and a little bit more. So roughly there, it doesn't have to be perfect, but. All right, and then we've also got 1.088, so that's about 1.1. So a little bit past 1, and then 2.954, so almost a 3. Not quite, but it's roughly in that little corner right there. We do want additional points because that wouldn't quite give us a good looking graph. So these are some nice points. We'll do negative 2, negative 3. Negative 1, 1. 1, 3. And I think that's the only thing that'll fit. So that'll have to do. Just make sure to look at this whenever you actually, man, I wish we could plot one past that. Let me go back to my table. 2, 13. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it'd be somewhere way up here. But okay, so we'll curve this up. Try to make that little S shape like that. Okay, so on this interval, we are decreasing because we start here, we're going down, and then we go up. So this is increasing. And then we go down on that little bitty interval right there, and then we increase again on the end. So we're going to decrease from negative infinity to the x-coordinate of this vertex, which was at negative 1.838. And then we increase all the way to 0, like that's the x-coordinate of the max. So we increase from negative 1.838, that's the x-coordinate of our minimum. All right, and we're going to go to the x-coordinate of our max, which is at 0. Then we decrease again on that little bitty interval. So it starts at 0, and then it goes to 1.088. And then we increase again from 1.088 all the way to forever, so infinity. Like that. So those are all filled in now. And I might do these two examples. Maybe I'll just do one more. Yeah, I'll do one more. Domain, I already know what it's going to be. It's always all real numbers. I'm going to go ahead and graph it. Negative x to the fourth plus 4x squared minus 3x minus 2. Okay, so we don't know the range. We know that it goes down to negative infinity, but we don't know the upper bound because I don't know what that y coordinate is right there. And this time it's not even a nice tick mark, it looks like, so I don't know, we'll have to see. Let's go and get the relative max. So we have two relative maxes this time, two hills. So relative max, we'll start with this one right here. I'm gonna hit the left arrow a few times and hit enter. I'm gonna hit the right arrow a few times, hit enter. Go back up to the top, hit enter one more time. So negative 1.5, I'm just gonna round to the 10th place on these. And you can too. Negative 1 point, I'll say negative 1.6. Y coordinate, we'll just say 6.5. All right, same thing. We got another max over here, so hit the right arrow. Okay, left bound point, go to the left. Don't go too far to the left because then you'll end up interfering with the minimum. So go just a little bit to the left of the max. Go a little bit to the right and then to the top. So we'll say 1.1 and negative 1.9. Like that. We have one minimum, it's this right here, that little low point. So second calc minimum. So this is the point we're talking about. Go a little bit to the left, not too far though, hit enter. Go a little bit to the right, but don't get in with that maximum. And then back to the bottom, so about right there. So 0.4, and then negative 2.6, like that. So let's go ahead and plot those. 0.4 would be just almost to the halfway point. Negative 2.6 would be about, you know, roughly there. Now we've got negative 1.6 and 6.5. 1, 2, 3, 4, 5, 6.5. And then we've got 1.1 and negative 1.9, so almost a 2. Like that. We need a few additional points, so go to second table. Negative 2.4 is a point. And so is negative 1.4. So is 0, negative 2, and 2.8. So I encourage you, any point that will fit on the grid, I encourage you to plot it because sometimes it's hard to know, like you want these to be accurate looking, so down. Roughly like that, oops. Okay, so my right tail, oh, all right, I messed this up right here. Let me go back to my table. That was a negative 8. To negative 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. All right, and at 1, it's at negative 2, right here. Okay. So something like that. Okay, that looks better. So in behavior, this tail is pointing down to negative infinity. The right tail is also pointing down to negative infinity. Now we've got our increasing and decreasing intervals. So we're increasing here, then we decrease, then on that little bitty piece right there, we increase, and then we decrease again. So increasing, we've got this interval from negative infinity to that first x coordinate of our max, which is negative 1.6. Okay, then we decrease from negative 1.6, and we decrease until we get to that minimum, which is at 0.4. All right, then we increase again from 0.4 to the top of that max. So 0.4 to the top of this maximum, which that x coordinate is 1.1. And then we decrease again from 1.1 all the way to infinity. Pretty tough. One thing about the increasing and decreasing intervals, where one picks off, or where one stops, the next one starts. So where I started here, it left off at the negative 1.6, this one starts, and then it goes to 0.4, and then it picks up at 0.4, goes to 1.1, where it leaves off at 1.1, this one picks up, and then it goes all the way to infinity.